all these homework problems are using the method of initial rates to determine the rate law. But I'm going to take you through them so that we can hit some high points and some key phrases that are necessary. Here's the first one, 1421. And for this reaction, we gather this data showing these 3 experiments and their initial rates. These initial rates are the appearance of NO2. So what is the rate law? First way I'm going to show you is that we can often do it verbally. So all we have to do in this case is compare different rates. So if we compare experiments 1 and 3, we see that the rate between 1 and 3 is 4 times faster. While what happens? This one doubles. Concentration of NO is doubling while the concentration of O2 stays the same. So since it's 4 times faster, when the concentration of one doubles, it's second order for that. Second order for NO. When I then look at numbers 3 and 2, this here, notice the exponent, 10 to the minus 1, is that the rate is only doubling. This time the NO is staying steady, and the concentration of O2 is doubling, leading to a doubling of the rate, so it's first order for O2. So that's how I get my rate law. K, concentration of NO2 squared, concentration of O2. But there's also a mathematical approach. And in that one, we see that we've got to make those comparisons mathematically. Now I'm still using the same ones I did before, rate 3 versus rate 1, that the rate law for each one is K times NO concentration to the X, O2 concentration to the Y, and by substituting in the numbers for rate 1 and rate 2, I come up with these values. Now here's the good thing, because since K is the same top and bottom, it cancels. Since the concentration of O2 is the same top and bottom, they cancel, including the Y. So I'm left with only this remaining. And remember that when you have a fraction, both top and bottom to the same exponent, you can rewrite it as the whole fraction raised to that exponent. So my 2 rates, that ratio equals the ratio of these 2 concentrations to the x power. A little bit of calculator work, 4 equals 2 to the x. So x has to equal 2, and the reaction is second order for NO. Taking the mathematical approach for O2, we find the same thing using rates 2 and 3, the same rate laws, but now when I substitute in, it is the NO term, which is the same and cancels out. Of course, the K's cancel out. So I'm left with just the ratio of the concentrations of oxygen raised to the Y power. And as before, this whole thing can be changed to the Y power, and we end up with 2 equals 2 to the Y. So Y has to be 1, and the reaction is first order for O2, and we get the exact same rate law. Either way is good when you can find those convenient doubling of reactions. So what are the units for the rate constant? Now, this reaction is third order overall. Remember, it was second order for NO and first order for O2. So that together adds up to being a third order overall, and the rate constant would be in the units m to the minus 2, s to the minus 1. Remember, whatever the overall rate order is, in this case third, it's just going to be molarity to the negative overall rate order minus 1, so that's why it's to the minus 2, and it's always seconds to the minus 1. Your last question is, what's the average value of the rate constant for these three data sets? So you've figured out the rate law. You have a number for everything except k, and you had 3 experiments. So each one of them can be solved. So I just substitute in the rates and the concentrations, rearrange it to solve for k, and I end up with these 3 numbers for my value of k. Find my average, I just add them up and divide by the 3 values. So I get 7,109 molarity to the -2 power seconds to the -1.